Fantastic. Well, first of all, thank you very much to the committee for inviting me. I'm sorry that I can't join you there in person. I imagine there will be some very interesting discussions after refreshments for the day after the busy conference days you have ahead. But I'll wish you well with that. And I really have a tough act to follow after Matthew's talk, but I hope I have something that will be of interest to this audience. And so the question, of course, is, could meteors from the DART asteroid impact reach the Earth, and what would they look like? So most of you will be familiar with this, but in case you aren't, the double asteroid redirection test was a spacecraft, better known as DART, which crashed into the secondary of a binary asteroid. So an asteroid with a small moon, if we can call it that. The secondary was called Dimorphos, still is called Dimorphos. The primary is called Didymos, and this impact occurred in September of 2022 at a relative speed of a little over 6 kilometers per second. So this was primarily designed to be a planetary defense exercise. That is, the mission purpose was to see if we could deflect an asteroid by crashing a spacecraft into it. This is called the kinetic impactor technique, and it was very successful. In fact, it deflected Dimorphos maybe a little bit more than we might have expected. That was quite exciting. But here I'm more interested in the possible extra scientific payoff that we could collect if meteors from this impact could actually reach the Earth. And I won't be giving away the punchline by saying yes, but probably in rather small numbers. But here I want to talk a little bit more about exactly what's going on and what would these meteors look like if they arrive at our planet. So here's, I'm not sure if hopefully the screen is visible and there's nothing blocking it. Please let me know if there are any problems with the view, but here you can see a summary picture of the DART mission. So here to the upper left, hopefully you can see my PowerPoint laser pointer, the main DART spacecraft, which was sent to crash into Dimorphos, the secondary here of our binary asteroid system. The choice of the secondary as the target was not an accident. It was very deliberate. And that's because a crash into the asteroid moon, in this case, will have a small change in the moon's period around the primary. And that will be much more easy to detect than a change in the asteroid's orbit around the sun. So there's some definite advantages to doing it that way. So that was deliberate. Over here on the left, you can also see an important secondary payload. This is the Licia CubeSat that was launched along with it and was released by the DART spacecraft. The European Space Agency's contribution, and very important to this whole process. So here's a diagram of the orbits of Didymos, which is shown in white. And then you can see the inner solar system there as well. The blue line is the Earth. If I zoom in a little bit more, you can see here the encounter circumstances or the impact circumstances. So this is near the time where the DART impact occurred. So Didymos was located here. The Earth was located here. This is not actually the closest point of approach of the two orbits. The minimum orbit intersection distance, or the MOID, is the location where the Earth's orbit and the orbit of the asteroid are the closest. The impact didn't occur exactly at the MOID for practical reasons. the observing geometry was a little bit better at this point and so forth. But you can see that the asteroid orbit passes relatively close to the Earth's orbit. It's about 16 times the Earth-Moon's distance, and it's near this moid where we would expect a meteor shower to occur if debris from this impact can reach the Earth. So here's just a quick, hopefully the video will be smooth enough. Sending it across the ocean, of course, is always problematic, but there you see the Lichia cube being released from the primary DART spacecraft. This is a computer simulation of what would have happened. Of course, the primary spacecraft is destroyed on impact, and so it can't really observe the after effects of its impact. Seen there, the ejected, the debris material is leaving, and then there you can see the Lichia cube probe passing by and observing exactly what happened and getting some very important information. So the data that came back, here are some of the key pictures, and they look a little bit fuzzy, but they're actually provide some very important information. So in both of these images, the larger white object is the primary asteroid at the center of the system, and then the smaller asteroid is down here. And then this gray material that you see spread out is the dust which was ejected by the impact. So you can see the impact was successful, of course, and a lot of material was released. This would be primarily small meteoroid, asteroid particles, which have the potential very easily to become meteoroid particles if they can reach the Earth. So this is where our work comes in. And these are just some of the technical details out there for any technically minded members of the audience. Details how we simulated the trajectory of these particles from the asteroid through the solar system and eventually possibly to the Earth. We, of course, have to consider the effects of all of the planets in the solar system, but these particles are small enough that they're also subject to the effects of radiation pressure from the sun and relativistic effects like Poynting-Robertson drag. And so all of this is accounted for in the simulations, and it means that particles of different sizes actually will travel on different paths, which is not true of a purely gravitational solution, something meteor scientists are very well aware of. So this is now going to be an animation of the impact, and this is the part where hopefully the ocean between us will not create too much of a problem, but I'll point out that over here, there's going to be a yellow circle, which I'm indicating with my pointer here, which is where the impact occurred. And then as we proceed, that point will remain fixed there for you to see, but will actually be advancing through time. So the cloud of debris is shown there in the colors yellow through blue. And those represent particles of different sizes. The legend is shown in the lower left there. And the camera is going to pan down a little bit so we get a better look at the closest point between the orbit of Dimorphos, and you can see the debris largely stretches out along that orbit and forms this meteoroid stream, which is close to, but doesn't quite reach the Earth's orbit. We'll play this again so that we can have another view of it. So the debris is ejected, in this case at 100 meters per second. We'll talk about what other speeds can do in just a few seconds here. But over the course of several years, the debris spreads out to form a meteoroid stream, which is near, but actually does not intersect the Earth's orbit immediately. Now, that doesn't mean that none of these particles can reach the Earth, but it's not quite straightforward to make this happen. So a little bit more detail. This figure that you're looking at here shows the time along the bottom. And so this shows how that meteoroid stream evolves over the next few thousand years. And in particular, this vertical axis shows how close it gets to the Earth's orbit. So if it gets well, to zero notionally, but less than 0.01 astronomical units. That means inside essentially the Earth, Sun, L1 and L2 points, we might see a shower. And you can see that the stream does, particularly for smaller sizes. These blue color represents particles which are only 10 microns in size. For these very small sizes, eventually that meteoroid stream will very slowly move over and intersect the Earth. But the larger particles that produce the more dramatic meteors, these sizes up here towards the top of the graph, actually don't really get particularly close to the Earth. This is for low ejection speeds, 10 meters per second. We explored a variety of different ejection speeds. 10 to 1,000 meters per second is where we expect the bulk of the debris to be produced. Here you can see some of the other ejection speeds. This one over here on the left, again, is the 10 meter per second ejection speed that we were just looking at. At higher speeds, 100 meters per second here in the center and 1,000 meters per second here at the edge. You can see the streams, again, do not get particularly close to the Earth, but as you go to higher and higher ejection speeds, it gets better in the sense that they approach the Earth's orbit more closely and they get there faster. But unfortunately, for meteor observers, the debris which is produced by that immediate impact of DART onto the secondary doesn't come very efficiently, at least directly to Earth. So does that mean we're completely out of luck? There's no chance of seeing meteors from this impact? And the answer is not quite. There is actually a possibility that meteors could arrive from this impact more directly. But the ejection speeds would have to be higher than is typically expected. And here I mean ejection speeds larger than about 5 kilometers per second. But this is not out of the question. People who do cratering of asteroids tell me that the fastest speeds you expect are speeds roughly equal to the impact speed. And remember, the impact speed here was 6.6 kilometers per second. So we might have a small fraction, a fraction of 1% of material which can reach these high speeds. And so this material is actually traveling even faster than the material I've already shown you. And this might actually do the case. So here we're going to watch another animation of the impact, in this case with the fastest speeds. So 5, 6, and 7 kilometer per second ejection speeds are going to be simulated. The DART impact will be here, and we're going to see the Earth across here, and we'll see how the material can reach the Earth. So let's just get this started. So the material is expanding after this impact spherically, and there you can see the Earth and its L1 and L2 points. After about 15 to 30 days or so, this material can arrive directly in our atmosphere. So if we were going to receive meteors from the DART impact, it is possible at these high speeds for material to arrive essentially directly from this impact and reach the Earth on a very short time scale. This is really our best opportunity to observe meteors from this impact. It's probably a small fraction of the total material, but it is possible. And if we could find this material, we would be seeing some very interesting material from the target asteroid. So what would this material look like? Has anyone seen it in particular? Well, specifically, the material, if it arrives, would arrive between 15 to 30 days after impact. It doesn't return again in later years like a recurring meteor stream, which is unfortunate. It means that most of these meteors would have already happened if they did happen. The radiant, we can tell you, it's in a right ascension of about 0 hours. But unfortunately, for most of us living in the northern hemisphere, the radiant was actually in the far south at a declination of about minus 50 degrees. Another disadvantage for meteor observation is that the speed relative to the Earth is actually fairly low, only about 9 kilometers per second. And even after it falls into the Earth's gravitational well, the in-atmosphere speed is only about 15 kilometers per second. So everyone in the audience will know that slow speeds like that mean less light production, less electron production if you have a meteor radar. And so these meteors are somewhat disadvantaged by their speed in terms of actual detection. The number of meteors that would actually be seen over the sky of any particular system is also likely fairly low, though there's a fairly large uncertainties because we don't know exactly how much material would be produced at these kinds of high speeds. So, of course, the question is, were any such meteors seen? That's a fantastic question. But as far as I know, none of them have been observed. But many people in this audience will know much more about meteor observation than I do. And if you're familiar with a meteor system, particularly one that can see a southern radiant, I would strongly encourage you to go and look in the database and see if anything might have been observed. And please let us know if that is the case. I will be very happy to send you more details about what exactly we should expect if you want to do such a search. But again, unfortunately, because the radiant is quite far south, there aren't very many systems that would actually be able to see these events. We also produced a new meteoroid stream. You saw those particles in space. Is that meteoroid stream dangerous to spacecraft? The answer is maybe slightly, but without going through this graph in any great detail, it just shows, well, maybe I should at least point out, the most important axis is over here on the right, and it shows how the density of material in that meteoroid stream compares to the sporadic meteor background. And so the density in the stream is actually fairly low for larger particles. This black line is 1 centimeter, and up at the blue sizes, 10 microns or so. That's the only region where the density of particles exceeds the sporadic background. So it's not a particularly dangerous part of space for spacecraft to travel through, but there is noticeably, or at least measurably in some cases, more particles than in the background. So wrapping up, most of the material from the DART impact is not expected to reach the Earth in any great quantity for thousands of years. If you're around in the distant future, we may get a new meteor shower, but unfortunately, it will probably be after most of our times. But there is a possibility that a small fraction of the material was directed to the Earth within a few days, 50 to 30 or so, but the fluxes are very low. There's a new meteoroid stream in our solar system as a result of the DART impact, but it is fairly sparse compared to many natural ones. And I sometimes get asked about whether or not we should be concerned about creating these new meteoroid streams. And I say, well, certainly this stream its abundance is quite low compared to other streams and compared to the background. But people often point out to me, and I agree with them, that this situation is similar to the space debris problem that we have in orbit of the Earth. When we first started to put satellites up in space, we didn't really worry about creating junk because, of course, there's plenty of room and it will never be a danger. 50 years later, this space junk is now becoming a problem, and that is something that we might want to think about before we create new meteoroid streams. But for the time being, the DART impact has not really created a problem as far as that goes. So some acknowledgements of the funding that was done here. I really want to thank the IMO conference organizers for inviting me and putting together this fantastic conference, and I'll be happy to take any questions. So thank you very much.
Yeah, time for questions. Oh, nobody yet? So, Paul, thank you very much for this talk. I have a question about figure 4. And one of your last slides was entitled figure 4, and that related to the density calculations and the danger to spacecrafts or satellites.
Okay, figure 4. There we
Yeah,
go.
this one. Yes, yeah, that one. So the question I have is this this graph based on purely a model, or is it derived from in situ measurements?
Yes, that's a great question. And this is purely from our model. So making some assumptions about the amount of material that was excavated. We know how big a crater the dark impact created approximately. And so knowing that amount of material and how it is distributed over time, we can model that. But as far as I know, no one has yet made any in situ observations of the dust in this stream, though that would be very interesting to know.
Yes, indeed. And do you know of any calculations being done before the impact? So, or in other words, has there been done any risk assessment for all the dust and particles you create of such an impact to all the satellites we have around Earth?
As far as I know, there hasn't been a formal risk assessment done. Obviously, um, the model results show that the flux is expected to be very low, but you certainly could worry about systems like the James Webb Space Telescope, which of course is an open design that has undergone meteor impacts before, and the instrument has actually been degraded to a certain extent by those impacts within expected tolerances. But the background or the flux from this impact at the James Webb Space Telescope or at the Earth is actually expected to be below the background meteoroid risk. So to answer your question, no, I'm not aware of a formal risk assessment, but some back of the envelope calculations show that the risk from this particular impact is quite low.
Yes, thank you. So I see there are no online questions so far. Yeah, Detlef.
This is Detlef here. Just a quick comment from what I learned working at the space agency. The flight dynamics people are always very careful about these things. And even though they were not doing any detailed modeling for these generated dust particles, in these cases, for example, when we looked at having a spacecraft monitoring the impact, flight dynamics was very insisting on hiding the spacecraft behind the main body. That was one of the reasons why some of us didn't really push so much for having a spacecraft to observe the impact, because we would have to hide anyway and not see a lot. Okay, you could argue you can always measure something. It would have been better. Similar for when there was this comet, I forgot the name, passing close to Mars. ESA timed the orbit of the Martian spacecraft as much as they could to have Mars between the cometary dust cloud and the spacecraft. Again, there were some, I think in that case, there were even studies done for the flux densities, but of course they are super vague. Anyway, the spacecraft operators typically force the scientists then to be as far away from the event and in a position where it's difficult to measure something. It's always a bit annoying, but it keeps the spacecraft safe.
Yes, I agree. Many of these predictions are necessarily somewhat vague, and the spacecraft operators tend to be very conservative and to act to protect the spacecraft as much as possible. It means sometimes that science operations get impacted, but yeah, I understand why they do it as well. Though sometimes I agree it might be better to get a little bit more science. But thank you for that.
Okay, thank you, Paul. Oh, are there any other questions? Oh, here. Yeah.
Before impact, we saw some pictures coming in with large boulders on the surface. Those large boulders could loosen. Is that any case interesting?
So we don't know exactly the sizes that were released from the impact, but yes, there could be some larger boulders. If there are, however, they're they're quite rare. We don't expect there to be enough of them to reach the Earth. That would be spectacular if they did. It would be great to see a very bright fireball or bolide from this impact. But the numbers are expected to be low enough that the probabilities are not very good for that. But yes, it is a possibility.
Okay, thank you.
Okay, last check. I see no other raised hands. So let's thank Paul again.